some predicted value y cap. This is my predicted value. I have 31 here. I have 32.1. I have 27. I have 27.5. I have 26. Now, if I should construct another, if I build another model and I got something like this, 32, 31, 28, 25, and 25.5. Which one do you think is going to give you? It's going to give you something like a perfect model, like a good model.
As compared to plain Y, right? As compared to that first column.
Yes, as compared to your first one, this is the actual value.
I think I'll choose the first one. Huh?
The first, you mean this guy? You mean this one, Abi?
Yes.
So why did you pick that? Why did you pick that?
It's somewhat closer to the original one, and the other one is having lesser value than some point.
Exactly. So that is what SSR is trying to catch. So that's why you have something like this for SSR. Why is this thing doing like this? SSR is saying that I have summation of y into bracket like this minus, and I have what's it called, b naught, the minority that's been, and then this is my model, b naught plus b1 x like this, all square. This is my error square, error sum square. So actually this is the iteration. This is your original y. This is your predicted y. This is your predicted y is b naught plus b1 x plus error. Abi, this is your equation.
Okay.
By the time you take this minus this, you're going to have e is equals to not this minus this, like y minus this. I'm going to have e is equals to, so I might have this one to be minus here, it doesn't matter. Y minus into bracket b naught plus b1x, not even minus, it's going to be positive because it's going to the it's going to the left hand side. So I'll have error to be y minus this. So by the time I square both sides, I'm going to have this SSR. It means it's calculating the error, that is this estimated, this predicted value minus this actual value. I'm trying to get what are the error, like the mistake, like when you do percentage error at the end. So what's the mistake? Okay, I wasn't able to get, and for instead of to get I got 31, the error is 1. By the time I square, I can have negative error because maybe I predicted more or I predicted less. So that's why we are doing the square of the thing. So the one that is smallest, that minimizes the error, will tell you the model that actually performed better. So that's, so looking at this, if you have the data to be very large, just looking at this, you'll be able to know which one is better, because this sample is very small. That's why you're able to tell that this guy is actually better than this guy. So by the time you have a large data set to predict, you'll be able to see this. So that's why this guy came into play. That by the time it take the error between the predictor and the actual value, and I square it, the one that gives me the minimum error is going to be the guy that is performing better, the models are performing better. So the lesser the SSR, the better the model. Do you understand now?
Yes. That's the lesser the difference between the original and the predicted, the better
Yes.
the.
So that's the point. So let me. So yeah, moving forward, the checking model accuracy. So for appropriate predictions for which regression models are used, we need to verify the adequacy the uh, of the models to analyze particular data sets. So R squared and adjusted R squared methods are used with are used to check adequacy of the model. So as we can calculate using this formula. So you have R squared to be equals to 1 minus SSR over SST. So we have what we call
Sum
this
of
is
square.
sum of square plus regression all over sum of square total. So we are going to see how this guy actually affects our model as we proceed in the. So you see an SSR sum of square regression are the total sum of the squares and the total sum of square error. This one is the error type, and this one is saying what's called sum of square total and sum of square error respectively. So you have SST sum of square total and SSR with the sum of square regression, which is the same thing as what we saw here in this
Yes.
slide. So you have adjusted R square. Now adjusted
So
R square, I think.
sorry, from the previous page, what really is SST? That's sum of squares of total. What total are we squaring?
So this sum of square total is like how do I explain this? How do I explain this?
So, but this formula is just used to check the adequacy of the model. From what?
Yeah, so this SST we usually calculate when you are doing what we call all these tests in statistics. But we are going to see how this actually helps as we proceed in the course. Okay. So we have what we call adjusted R square, which uses the R square as in the formula. So this is adjusted R square, this R square. So adjusted R square takes is being used when you are trying to like adjust your model. Let me put it that way. Like, okay, in some instance, you want to build a regression model, you might do all in, or you can do start building from up down or down bottom up or top bottom. So what do I mean by that? Sometimes if you want to build a model, you can put all your x's, all your independent variable into the model. Are you with me?
No.
Then you build your model based on all the dependent variable, all the independent variable. Then you start optimizing the model by dropping variables that are not significant in the model. In that case, you'll be seeing adjusted after you calculated. Sometimes you can use the p value and the likes of that. But I think you are going to see that as you proceed also. So you use some certain criterion to see which variable should I drop that does not improve the model and stuff like that. And that's called backward, like it's called backward elimination method. And we have forward the forward process whereby I will start with one variable at a time. I'll start with a variable that actually has a strong correlation with dependent variable or the response variable. I will start adding uh, new model into the new variable into the model based on the adjusted R square. You say, I think this variable is going to improve the model that I include it to the R square does not improve any longer. There is no significant uh, there's no significant how do I put it, difference between adding new variable or from the previous model you have and the model you now get when you add another variable. So you just stop adding variables at that instance.
I don't get. Let me not lie.
This one is the forward process or the backward process.
Okay, so what's the purpose of this formula? Let's
So
start
this
from there.
so this one too, we are going to see how it relates as we also move this. I'm just trying to give an overview.
So if you see later, it will help me in understanding it.
Yes, exactly. So adjusted ASCII polling properties, it depends on the number of explanatory variables. It imposes a penalty, reducing R squared for additional explanatory variable. I'm going to see this also. Can you give me just 5 minutes?
Okay.
Okay.
Backward.
Yeah. So in here, so to build regression models, there are some assumptions you are going to uh, take into consideration. You assume that there's a linear relationship between your dependent and independent variable. So when I say linear relationship, it has to be, by the time you draw your scatter plot, it should form something like this. Something like this,
That joins.
like maybe there's increase in x cost and increase in y, or increase in x cost, decrease in y. You have a linear relationship between both of them. And independence, assume there is no correlation in the errors of the collected samples, homoscedasticity and normality. Assume there's a normal distribution of errors in the collected samples. Normality that spoils the normal distribution. So these are the 4 assumptions you have to consider. You might not have to talk to you about this. Okay, let's talk about it. Now we have what we call multipolarity. So what's this multipolarity of a thing? You don't want to build a linear regression model with 2 independent variables that are strongly correlated with your y. So what do I mean by that? Let's say you want to build a model y, and you have 2 x's, say x1 and x2. However, those x1 and x2 are actually very strongly correlated to your y, like they are similar. Like if you do correlation between x1 and y, it has like 0.90 correlation, and if you do x2 and y, it also have 0.9 something correlation. Like they actually predict y in sync. in similar manner. So if you have those two models, those two independent variables in your model, it might affect your model anyway. So muscularity is a non-linear relationship between two explanatory variables leading to inaccurate parameter estimates. So two or more variables representing an exact or approximate linear relationship cause multiplication. So two or more variables, say one x1 and x2, having a linear relationship with y may cause um, your model not to do well. So multiplicity can be detected by calculating the VIF with the help of this formula. So essentially, Ri is the regression coefficient of the explanatory variable with respect to all other explanatory variables. So let's say, for example, let me see the next slide. Okay, I think they give an instance in your textbook for a particular variable. So if the VIF is like is it equal or greater than 5, you say that the model has multiple linearity in that regard. I think you have a book with you. You have a material with you.
Yes, which one? The lab book.
The book too, I mean.
Grab.
So I think if I should go to what is it called? Okay. If I go to page 13, you see it there. So if the VIF is high, 5 or above for the regression model, the VIF is used to identify the presence of miscurrency in the model. So we have a VIF of 5, then it's because there's muscularity exists in the data. That regard. Okay. So those some of the effects of muscularity are inability in estimating standard errors and coefficients, high variance, ordinary square causes problems in assessing the estimate. So the whole idea is that you want to avoid multiple linearity
Hello?
in the data set. Hello, can you hear me?
Yeah, please, can you give me 5 minutes? Let me change my location.
Okay.
Let me check where I'm sitting. Yes.
You have to. Success. Hello, are you there?